So hello, everyone. Empowered Networks would like to welcome you to our webinar today in collaboration with Microchip Technologies and Greyware Automation. We'll give everyone just another minute to join. Thank you. Okay, before we get started, I'd like to go over a few agenda items. All of your lines have been muted to reduce background noise, and we encourage you to submit questions via the Q&A feature found at the bottom of your screen. We will do our best to answer all questions. If we don't get to your question, we'll be sure to follow up and answer it offline. Also, all presenter contact information will be made available at the end of the presentation. This webinar is being recorded, and a copy will be emailed to you. At this time, I'd like to hand it over to Maroon Ayub, Director of Empowered Networks, Network Timing and Synchronization Practice. Thank you, Maroon.
Thank you, Jenna. Welcome, everyone. Thank you very much for joining us today and focusing on NTP today. But I just want to take a couple of minutes to introduce myself and the team. My name is Maroon Ayub. My areas of focus is synchronization in Canada, more on the sales side. And also, we have joining us today is Paul Skoog, is a senior product manager of Microchip. Will be leading the conversation today around the importance of NTP in an enterprise environment, or importance of timing, I guess. Also, his teammate for today's activity is Steve Ratzlaff, and Steve is a senior director at Greyware. Will be talking to us about time distribution and monitoring. Next slide, please. Empowered Networks is a value-add reseller, as I mentioned, where my focus personally is on the time and synchronization piece of our business, but we also focus on a couple of other areas. One of them is network monitoring, security and compliance with our partnership with great companies, great solutions, best in class. We wrap these great solutions with our integration and support services to provide the best solutions to our customers. Next slide, please. This is a full overview of Microchip's portfolio that Empowered focus on in Canada. We've got solutions from to satisfy the carriers from their 5G deployment projects that's going on, right down to the oscillators that go into the switches and routers. So all the embedded technologies that you might see in the field. Today's conversation, as I mentioned, of course, will be focused on the enterprise and the importance of timing within the enterprise environment. And on that note, I'll hand it over to Paul Skoog to lead that conversation. On to you, Paul. Thank you.
Great. Thank you very much, Maroon. So let's just jump in and look at the agenda here for this conversation today. So let's start with why network timing in the first place. We'll move on to where timing is used in the enterprise. We'll talk a little bit about free time from the internet. There might be some things that you never realized when it comes to that. We'll talk about some essential aspects of the network time server, the source of time for the network. But then we've got some good conversation to go on here around distributing the time across the network, as well as monitoring and auditing it. So some things to be learned there as well. We're going to give you a little preview of some brand new technology at the end of the presentation. I think you'll find interesting, some interesting data to look at there. I think that as well you'll find surprising. Then we'll just wrap it up with some Q&A and go from there. So with that, let me just start right in here. Why network clocks to begin with? Why clocks? What's the problem with clocks, right? So the biggest problem here is that they use a quartz crystal. Okay, you find them in every router and server and switch and your smartphone and everything else. They're all using these little quartz crystals to keep the time, and they work, famously, except for two problems. One, the quality varies, but also, quartz has a characteristic that it's temperature sensitive. And when the temperature changes, so does the frequency of the vibration or oscillation of the quartz itself, which means when the temperature changes, the clock can speed up and slow down. The other thing is that quartz ages. Yes, quartz crystals age, and over time, the frequency changes. So just by the mere fact of the way quartz behaves, you're destined to have problems keeping correct time. And that leads to the big problem here. And that is you have all these servers and routers and so forth. They're all keeping the time. And even if you set the time to be the same initially on all of them, they're all going to drift off at different rates. And there you have it. It's kind of like herding clocks. So that's the problem we're trying to solve. So when it comes to time in general, it occurs all over the place, right? I mean, it gets used in, secure communications and financial exchanges and data centers. And so what we're here to talk about today is using time in the enterprise, okay? Because applications all across the enterprise need accurate time. So the overarching statement here on this is that accurate, secure, and reliable time is necessary for all those devices I mentioned for improved network operations and business operations. So the number one reason that we are continuously told that folks in the enterprise need accurate time gets down to log file timestamp accuracy. And the better resolution and the more accurate they are, the better off your network management system reporting is going to be. Because at some point in time, you may have a fault and you're going to need to go look at those logs. And that's when you really hope they're high integrity, all the timestamps line up properly, and you can quickly resolve the problem rather than finding out the timestamps are wrong. And the first thing you have to do is sort out the clock differences to get the logs to line up. So at any rate, log file timestamp integrity is the number one reason why people deploy NTP into their network. There's also network security. You may or may not know that Windows clients and servers actually can check the time one to another. And if there's time alignment close enough, then it'll authenticate. It uses a technology called Kerberos. And if I had more time, I'd tell you about a catastrophic problem that occurred one time to a major corporation when they lost authentication and had millions of grumpy customers. At any rate, moving on. Real world time values. Humans like to see the right time, generally speaking, on email servers and their workstation clocks and so forth. So having the right time in general is just a good practice for us. The next one, network operations. And this is a big one as well. One of the growing areas where network time synchronization is really important is in distributed database applications. They work much better when they're in time sync than when they're not. The other is legal regulatory. You may or may not be subject to what's known as PCI DSS. Payment Card Industry Data Security Standard. It has requirements for running NTP and security and everything else. So those are the high points where we need accurate time. But first, I kind of wanted to talk a little bit about the progression an organization might go through. Imagine the triangle is all the network out there in the world. You've got small ones, medium ones, and big ones. And generally, if it's small network, timing is not so critical, okay? But as the network grows, you have more devices on it, more servers and workstations. It's appealing to go get free time off the internet. To be sure, it's free, and what's wrong with free? But as an organization grows and that time becomes more critical, that's when you need to think about getting a network time server. It's more essential that time be correct. Okay, so why would that be? What's wrong with free time from the internet? So let me walk through this here just briefly, just to point out a few things about it. And one of them are security risks. Okay. You have to open port 123 in your firewall to two-way traffic. Keep in mind that time source is not your clock. And whoever's clock it is may not be particularly concerned about maintaining it or the security surrounding that clock. So you effectively have no control where that time server is even getting its time, where it's located, anything else. You may have just grabbed an IP address out of a pool. You also cannot authenticate to it, which means it's subject to a potential man-in-the-middle attack because time is sent in the clear in NTP packets and they can be modified. There's also accuracy risks. You have no assurance that time's correct. Again, it's not your clock. You don't know where it's getting the time. Okay. Is it stratum 1 or stratum 14? You really don't know. And that introduces also, since you're going out over the internet, the notion of asymmetric delays. So you may think you're accurate in terms of time, but asymmetric delays across the internet may be skewing that time to an accuracy that's not acceptable. And lastly, there's just flat out reliability, right? An internet time server is not going to send you a trap or an alarm if something's wrong, okay? You're likely competing with other people to get time from the same one, which means sometimes when you may go ask the time, you may not get a response, okay? It may not be reachable. And so there's no assurance of sustained responses. So that's something to think about with free time from the internet. And of course, our answer to that is going to be an enterprise network time server, right? A GNSS reference, Stratum 1, NTP or PTP network time server. So let's just pause a little bit right here and take a look at one. In case you're not familiar with it, what we're looking at here is a Sync Server S600. It is a best-in-class NTP time server. It is also a PTP Grandmaster. It's a 1U device, about the size of a pizza box, and obviously keypad and display, which is primarily useful when you pull it out of the box and you get the thing up and running real quickly. You get an IP address to it. Can also be useful if the time server sits in a faraway data center and for some reason you want someone to walk up to it and give you some status information off of it. On the backside of the unit, I'm not going to go into great detail on it, but I'll just point out the fact that there's 4 ports there. And that is very useful for timekeeping, adapting to your network topology, as well as security. It's a big security add as well. The primary user interface on the product is a web GUI, which customers really love. It's you don't need the manual. It's very intuitive. You just walk your way through it. So lots of good feedback on how easy it is to just set up the device just through the web GUI itself. So I thought I'd just share with you, I'd take the lid off of this thing. And this is what's inside one of these things. You got a really high capacity motherboard that can do a lot of time stamping. There's a GNSS receiver in there, can handle GPS as well as other constellations like GLONASS from the Russians and Galileo from the Europeans and so forth. Single or dual corded power supplies. That's a reliability aspect. I'll talk about that. You can put in a rubidium atomic clock in here, okay? Which, by the way, I have upcoming here in just a couple slides. I'll give you a little tour of one of those. It's actually kind of fascinating what's in there and how they work. And of course, hardware time stamping on all the ports. That's a really big necessary plus if you're going to operate as a PTP Grandmaster. So with that, generally, when you have these kind of conversations about network time synchronization, one of 3 things is going to be important, all right? Accuracy, security, reliability. It comes up routinely. For example, in talking to someone from a big bank, security and accuracy is very important, especially security, which of course I'm glad about because they have my money. But nonetheless, they do a great deal of testing on these devices, both from an outward standpoint, but then they'll log in and continue to test it and try and find vulnerabilities in it. And they give us feedback. And so over the years, this product has become extremely secure, very well hardened. Similarly, accuracy and reliability are going to be important to someone like a stock trader, right? They need accurate time, but they need it to be reliable for 2 reasons. 1, they want to make it through a trading day with accurate time. And 2, they're held accountable to various different audit standards and requirements where they have to prove that they were accurate. So reliability is a big deal. So let me just walk through each of these just briefly, and we'll talk about accuracy. And sometimes accuracy and precision kind of get mixed up a little bit. So the little targets over there on the side give you an idea of the difference between accuracy and precision. And of course, on a sync server, the big idea is that we are precise and accurate. And in this case, it's accurate to UTC, which is the time used on all servers, workstations, your smartphone, everything. It has UTC on the inside. And this clock, the sync server, is accurate to 15 nanoseconds to UTC. And typically, it runs at about 5 nanoseconds to UTC. Very accurate clock. But with that, customers want assurance of accuracy. And sometimes, since you're getting time from GPS and disciplining the local oscillator, you may turn out that someone accidentally disconnected the antenna cable, or lightning hit the building and that it damaged the cable or the antenna, but you still need accurate time. And that's where the oscillator comes in. And you can go with a standard oscillator, which if you disconnected GPS, it would keep about 400 microseconds a day, okay, slowly increasing. That would be the drift rate of that oscillator, because remember, the oscillators drift. You can upgrade it with a better oscillator like an OCXO, or you can put in a rubidium atomic clock, okay? And remarkably, they're not that expensive, but it'll keep the time to a microsecond a day, less than 3 microseconds over 3 days. And the big idea here is simply put down in that little sticky, and that is atomic clocks buy you time. If you have to maintain a certain accuracy to UTC, okay, and something happens to the signal, like I said, damaged antenna or something like that, you can just be in holdover on that atomic oscillator. The network will be kept very accurate, and you can, you've got a couple days, to get a new antenna and go up there, screw it on and that kind of thing. So at this point, I thought I'd digress just a little and give you a little virtual tour of a miniature atomic clock. So I took the lid off of one, and you can see they're not very big. They're only about as wide as a couple of quarters. And the atomic element that we use in here is rubidium. So let me just give you a little tour around this device. So inside that metal can, okay, and that is actually, it's a microwave cavity. Inside there is a glass bulb, and it's a clear glass bulb, and it's filled with rubidium atoms, okay? And so that little glass bulb sits in that little microwave cavity, and there's a little window in the side, okay? And you can actually see a little bit of the glass there. And this little device here is a light cell, which generates and shoots photons at that cavity, all right? So it's sitting there shooting photons right in through the window. And on the back side of that cavity, we get a photon detector, and it's measuring how many photons make it through the glass bulb with the rubidium. So the big idea here that the smart guys figured out, okay, has to do with the fact that they discovered that rubidium absorbs photons at a very precise excited state frequency. Okay, so inside that microwave cavity, we excite that rubidium gas up to a quantum state where it really wants to absorb photons, and we know we have that frequency dead on by a little feedback loop from the photon detector. So as a result, we get a very stable frequency that's useful to make a very stable, clock for purposes like a time server for holding the time accurately for a long period of time. So anyway, let's move on. Let's talk a little bit about security. So in this case, certain security advantages offered by the Sync server has to do with both timing and management. There's a little drop-down menu in the product itself listing all the different types of security things that are available. I mentioned the 4 ports were important. That is because only LAN 1 is used for management, and it can also be used for timing, but LANs 2, 3, and 4 are timing only. And that allows you to take the first step in security, and that's segregating, out-of-band management from in-band management. And, you have the service ports for everybody in the organization getting time off 2, 3, and 4, but you're able to manage it on LAN 1. So that's the first step in security, and that's a separation. And there's other things as well. We protect the CPU from denial service attacks. We can put in X.509 certificates for the web GUI. We have authentication for TACX and separate control lists. So you get the idea. There's a lot of things in here to make that thing secure. And also when it comes to the timing itself, we have some reflector technology. We support authentication and so forth. So we put a lot of effort in making sure this is a very secure device. If we move on to reliability, reliability is more than just, hey, it's got a good power supply. It's about timing reliability. And that means that you're getting accurate time when you request it, right? We can have huge bandwidth on the product in terms of how many requests that we can handle. We cross-check the time. There's multiple constellations you can get it, because the big idea is you want an accurate timestamp from the device, from the Sync server when you request it. And similarly, there's a lot of design reliability that goes in as well. We're quite proud of it. One of the things is we put in a very wide temperature range requirement which is probably irrelevant if you're in a data center. But when you have such a wide temperature range, it means that the components that we had to use are higher quality, which gives us a better MTBF. And the MTBF on this device is greater than 25 years. Very reliable. So we're very pleased with that. So just kind of wrapping up this section here on the Sync server itself, like I said, this is a best-in-class Stratum one-time server. It provides a lot of benefits in terms of the accuracy and the holdover that's available. 4 ports standards is a very big plus. There's a lot of built-in hardware that's enabled through software options, a lot of security hardening going on. That's just an ongoing thing with the product. So as a result, it's a very reliable source of time. And of course, it's very easy to use, which is a requirement that we all want out of a device like this these days. So with that, I am now going to hand it off to Steve Ratzlaff to talk to you about network time client management and timing accuracy.
Oh, great. Well, thanks, Paul. I appreciate the information you've shared with us so far. It's very interesting. What I'm going to talk to you about, you go ahead to the next slide, I'll get started. As Paul said, my name is Steve Ratzlaff. I am Director of Marketing and Sales for Greyware Automation Products. We manufacture a product called Domain Time 2, which is a time distribution and monitoring, management, and auditing system that is designed to reliably, as Paul has said, accurately, securely, and reliably distribute time throughout the network. What you see on the right here is one of the many different time distribution hierarchies you might see. This is typically what you might find in a Windows environment, where time is coming from your reliable time source, in this case, an S600, to a primary domain controller, which then distributes time to the secondary domain controllers, and then the end unit devices, clients get their time from those devices. So domain time can take over those roles as needed. The domain time is made up of 4 components. The time client is the bottom level piece that synchronizes time, and we can do it via various protocols, PTP, NTP, or our own DT2 protocol. And we can also do authenticated versions of that as well. So you have additional security you can add. We also have similar protections against DOS and other issues as well. The server component is very similar to the client, does everything the client does, but also can serve time to other devices. And that basically allows you to put a secondary server anywhere you need one, so that you have local sources of time easily available. The other portions of domain time are the central management and auditing pieces. The manager component is a single pane of glass control panel that lets you see all of your time devices, easily install to them, upgrade them. And one of the very important features of that is that you can easily manage them. The more machines you have, obviously, the more problems you have in keeping them configured the way you need them to be, or as you bring new machines onto the network. That's always a challenge. Well, the manager has the ability to create templates to easily manage that process. Let's say, for example, you have a data center in New York and a data center in Chicago. Well, clearly, you want your machines in New York to synchronize with New York servers and Chicago to synchronize with those that are local there. A template would allow you to apply easily to all of the machines in New York, tell them all to use the New York servers, and you can have a second template available for Chicago. You can roll that out as needed, or it can be applied to machines as you install them. And that means there's no individual configuration or touching of machines needed. And then finally to that, we have a plugin component called the Audit Server, which I'm going to talk about quite a bit more in detail later on. So we'll go ahead to the next slide. I mentioned domain time is optimized to easily fit into your environment. Everybody has different requirements and different hierarchies on their network, different sets of firewalls and locations. Domain time is flexible enough to handle that. We have clients for Windows and Linux systems, so you can use your existing machines, and you can manage the machines the way that you're used to managing them. And it's also optimized to provide the best performance on whatever type of machine that you're using. Typically, you have either physical machines or you have virtualized machines. And I want to talk a little more about virtual machines because they present a particular challenge for timing. In a physical machine, you have many applications competing for the same hardware. And so you'll often see some time drift or excursions because an application is busy and it's not letting the clock advance. Well, that problem is magnified and multiplied in a virtual machine because you not only have other applications, but other entire operating systems competing for the same hardware. So you'll see a lot more time drift, a lot more excursions, and more headaches in trying to keep time accurately in a virtual environment. That's becoming ever more critical as people are moving to cloud. Cloud systems typically are virtualized, and you may be already using virtual systems in your data centers. So you may be running into these issues. So domain time is optimized for those environments and able to take care of that kind of challenge. So we'll go on to the next slide, where I promised I'd tell you a little bit more about Audit Server. Audit Server is kind of the beating heart of making sure that the systems you have are operating correctly and that you're able to prove it. Domain time is designed from the ground up to provide telemetry back to the domain time audit server. What that does is allows you to collect synchronization information off of all of your devices in a central location, and that gives you historical records. So if somebody needs to know, or let's say you have a major event on Thursday at around 3 p.m., you can use Domain Time Audit Server to go back and prove what the condition of synchronization was on any of the machines in your network at that particular time. Or you have an auditor who needs to know, we have a transaction in question. What's the state? Well, you can go back and get that information very quickly because we've collected it all for you. In addition, we generate the kind of reports you might need in those kind of environments. A lot of people have issues where they need to report every day on what the state of their synchronization is. Well, this allows you to generate those reports. In addition, we allow you to reference that time to something else. If you need to prove your machines are accurate to UTC, Domain Time will provide that traceability and audit path to prove that you have UTC time on your machines. And then we also have the ability to handle disaster recovery circumstances as well. That's Audit Server. And then the next slide. The biggest question that we get is how accurate can you get with domain time? And unfortunately, that's a complicated question. One of the main issues in deciding what's possible is the kind of operating system you use. And that's what this chart is for. It shows you in an order of increasing accuracy what you might expect to see on particular operating system, going from older legacy systems all the way up to current systems using modern operating systems. And of course, in an ideal world, we'd all be using the latest versions of the OS and the latest versions of hardware. But unfortunately, in an enterprise, that's certainly almost never the case. You'll have older legacy systems that need to be maintained, or you're in the process of an upgrade. So you need to have your machines performing even in those kind of environments. And that's what you see here. Domain Time supports machines in all states of upgrade, from the older legacy systems to the most modern. This is what you might see as performance for it. Using NTP, the NTP machines are all in blue. You can see the older legacy systems were very poor at keeping time, but still, with Domain Time, you can get fairly significant improvements. But the later versions of Windows and the latest versions of Linux are able to get much superior performance, about less than half of 500 microseconds on Windows. And with hardware timestamping, you get the ability to get to about 10 nanoseconds on Linux. PTP gives you additional accuracy through better synchronization and latency measurements. So you can see in black, those are the same sort of machines performing using PTP. And I want to spend just a second to talk about the last column here, excursions. I mentioned that time is susceptible to disruption on operating systems. Most operating system clocks internally are maintained by the software as it runs. So if something interrupts your processor, your system clock can drift, and sometimes quite dramatically. We call those excursions. Certain operating systems are more susceptible to them than others, but also your operating environment contributes to that dramatically as well. And every operating system, even though it may be the most latest and greatest, is going to have those kind of excursions. Perhaps a network packet gets dropped, or some application hogs all of the processor time, or it's doing a disk transfer. And so it's very important that time, if you're trying to keep accurate time, that your time service is aware of this and corrects for it. Unfortunately, most timing services aren't very good at that. And that's what I'm going to cover in the next slide. Windows Time has a pretty well-deserved reputation for poor timing, even though Microsoft has made great strides in improving it in their more recent versions. They're claiming now that they're able to keep a 1 millisecond target using their NTP synchronization, and that's technically true on a machine that's in a steady state under no load and isn't encountering any kind of network disruption. But of course, none of us live in that world. And so what you also see is not only that it's susceptible to disruption, but it's very slow at responding to disruptions in order to correct it. What you see here is a startup of a Windows time service, correcting a time of about half a second, which is not that much. You can, at a machine startup, can sometimes see startups at order of days even that you need to correct. But it took this machine 51 minutes to bring the time under 1 millisecond. And that's bad enough if that only happened at startup, but unfortunately it doesn't. It happens anytime there's a excursion to the time, anytime during the day. Windows Time takes a long time to notice, takes a long time to correct it. It may not take 50 minutes, but it will take an extended period of time. And even that is bad enough. But in the Windows timing architecture, it's cumulative, this kind of error. Your PDC will take this time to respond, but your backup domain controllers have to take the same kind of correction. So they will take an additional amount of time to bring their time correct. And again, it propagates down through the network all the way to the clients. And believe it or not, on a large forest, distributed time can actually take up to 10 hours for a correction to propagate all the way down to the final machine on the network. That's not only true of Windows Time, but also true of other timing systems on other devices. Even on Linux machines, you may know that a lot of time daemons have to have their time manually set before they start synchronizing, or have to be within a certain time range before they're able to synchronize. And then they also have issues with handling disruptions. Can take a long period of time to correct. Domain time has been optimized to avoid that. We can correct at the maximum rate available on the operating system. So for example, the graph below is showing you that same 2019 machine correcting a similar amount of correction, but doing it in less than 10 seconds. Very impressive. Okay, we'll go to the next slide because I have a little bit more data for you. I mentioned that virtual machines have particular challenges. For example, on a physical machine, you'd never be able to simply just pause it, have it resume in an easy manner, and have the application not know what's going on internally. But that's what can happen quite often on a VMware or any other virtual machine. It can be paused. It can be moved from one virtual or one physical host to another. And the operating system and its applications have no idea that that's happening. Unfortunately, that means the time service doesn't know either. And therefore, let's say you pause a machine for 5 seconds. When you bring that machine back up, the actual clock is going to be off by 5 seconds. But the timing service doesn't know that, and it'll just happily do its thing until it suddenly notices that it's that far off and then try to correct it. Where domain time is optimized for virtual environments, it understands and knows about those kind of things. It recognizes a hibernation recovery and resynchronizes immediately. So you don't have that long limbo period before it can know what's going on. In addition, we handled the regular excursions and the performance of the machines at quite well. As what you see here is domain time on a Windows server with PTP synchronization, keeping about 6 microseconds. And you have a Linux on Red Hat 8, keeping about 2 microseconds, even in a VMware environment. That's very reassuring for those of you who are working with cloud or virtual machines. And then my last bit of data for you on the last slide is what you would see on a physical machine running the domain time Linux client. This is kind of the best of both worlds. Linux, one of the main advantages it has is it has built into the operating system the support for hardware timestamping. And hardware timestamping allows you to know how long it takes for a packet to go from an application all the way through the network stack onto the wire and how long it takes to transit the wire and back, which allows your timing service to know precisely what to correct for. And that's why you're seeing such dramatic improvements in Linux timing. What you're seeing on the top graph is on NTP synchronization from Linux, keeping in about 10 nanoseconds with very precise grouping. And that's just for an NTP, but synchronization is really phenomenal. And the bottom chart is that same machine using PTP, keeping an average of about 4 nanoseconds. So to summarize, we have stellar performance with easy to use, easy to install and manage software, the ability to know that it's operating correctly, to be alerted. And I didn't mention much about alerting, but you can set thresholds to be told when machines are off. And you can send alerts to your network management systems and anyone else who needs to know. And you have all of that wrapped up in a unified system. So that's domain time. And at that, I'm going to turn it back over to Paul.
Thank you very much, Steve. I think that it's really fascinating seeing this data, especially when you have like a Sync Server S600 that's timestamping in the low nanosecond range, and then you can see what's possible here on like this data we're looking at right now. It's really phenomenal how far we've come and how well we can keep time these days with the tools and products that are available. So thank you for that. I appreciate it. Moving on, I just wanted to give everybody just a glimpse of a recently released option on the Sync server. It's called the Blue Sky option. And what this is all about is GPS jamming and spoofing detection, protection, and analysis. You may or may not be aware that, over the years, GPS has sort of come under attack, certainly in certain parts of the world, certainly to jamming and some spoofing. Sophisticated countries can spoof it. And then you have commonplace jamming where, taxis have jammers to jam the Uber drivers, okay? That's just the world in which we live. And so when it comes to a time server that's just sitting in place, we want to be able to protect that thing. And the first step in protection is detection. So we can detect jamming and spoofing. We validate data coming down from the GPS satellites so that we know there's integrity in it and nothing is suspect. We also measure the local RF interference because it's different with every installation. So you want to be able to customize your alarms to your local RF environment. And this all leads to protection, right? If we detect something is wrong, we want to be able to disconnect GPS, if you will, and fail over to either alternative sources of time or go into holdover, like on the Rubidium. And then the big question is, if an event like this happens, you may want to go, well, what happened? And you want to be able to look back in time. And that's what we allow you to do with this option, is because we continuously record a whole lot of GPS information and RF variables, if you will. And we provide that in charts and graphs so that you can look back in time and see if something happened in the local environment that you can correlate to an alarm on the Sync server. At any rate, when we look at these, I thought I'd just give you some examples of what you can see. So on the left, I show an example of a poor antenna installation because, in general, you want the antenna to be in a good spot to begin with. And this is what a bad spot looks like. We provide what's called a cumulative site survey. So within about a day, you can get a graph like this. And this is a good example of everything that's wrong. This antenna is mounted on a railing of a tall building, and the building is next to a hill, and the city that it's in is in the very, very far north latitudes. And so when you look at this, it's a polar plot. The red segments are where there's a lot of satellites being seen because, satellites rotate, they're medium Earth orbit satellites, so they're always moving. And so we can see in these particular segments that are brighter red that we see a lot of satellites there. Blue means we don't see very many, and black means we see none at all. So black in this case is all right because that would be over the North Pole, and those satellites don't fly directly over the North Pole. So that's an okay thing. And actually, when we look at higher on the chart, those are satellites. This is in Norway, by the way. If you're in Norway, you can actually see GPS satellites flying over the Pacific. But the big idea here is these blue segment where we don't get hardly any satellites, that's because the building is in the way. And then there's a hill in the way. At any rate, if we look at some of these others, this RF interference jamming, receiver jamming, this, if you were to look closely at it, is interference caused by my iPhone 8 Plus whenever I walked into the room. Turns out the Wi-Fi, for some reason, causes interference. Now, granted, we're all in one room and the phone is close to the antenna and so forth, but you can see when I'm working in the office and when I wasn't in the office. You can see where the weekends are. The point being is if that interference continued to grow, pretty soon you'd be able to correlate it to some jamming problems. In this case, the interference is low enough where we could see it, but the receiver accommodated it, no problem. Here's another one down here. In this case, the red satellites, this is a chart of tracking satellite constellations. You can see here that all of a sudden the red bars, which were the GLONASS satellites, suddenly pretty much stopped. And when I discovered this, I just said, well, wow, something happened. I'm wondering why I don't have any GLONASS satellites. I look at the data and I find that all of these GLONASS satellites stopped being tracked the moment I turned on my brand new Motorola cable modem Wi-Fi router. For whatever reason, they were in the same room. They were too close together. I'll give you that much for sure. But when I turned it on, I lost the GLONASS satellites. So, of course, I moved the antenna and they all came back. But the point being is external events can be recorded and you can correlate them possibly to known events. So just sort of showing you just the resiliency here of, sync server time and frequency. We have an anti-jamming antenna option, which essentially any jamming signals coming from below the antenna, which typically that's where they come from because the antenna is mounted on the roof, it just blocks all those. So we get a lot of good, strong signal from the satellites coming in. You have the blue sky technology that's protecting for what's coming into the receiver. If it detects a problem, we can flip over to the installed oscillator and perhaps, an installed rubidium atomic clock kind of thing. And we can even have even more robust atomic clocks in there if it's a really important application. So with that, it's pretty much time for the wrap up. So I just wanted to just give you a quick summary here of what we've talked about here today. And I think the chart is the graph is a good summary, if you will. You need an accurate, secure, and reliable source of time to begin with. Okay, if you're getting time from the internet, I'd encourage you to investigate looking at getting a dedicated network time server, a Stratum 1, and the advantages and benefits that are provided by that to your network. And then, of course, you are going to need to distribute the time. Because the time server, you plug it in and it's wonderful, but your time clients have to be requesting the time from it. And so that's where the product domain time 2 can come in to give you really accurate time on Windows and Linux across the network. And then It makes it a lot easier when you can manage that time easily. And of course, if you're being held accountable for that time from an audit standpoint, that's where the audit server can come in, where if for say, MiFID II compliance or whatever, you have to demonstrate that you were in compliant in terms of a certain time accuracy. That's where the audit server can come in. So at any rate, it's a full reference source down to the clients to do the synchronization across the entire network. So with that, I think we're ready to open it up to any questions that we might have out there.
Thank you very much, Paul and Steve. Great presentation. My name is Corey Vitale. I'm a systems engineer with Empowered Networks, supporting the Microchip product line, and I'm going to help moderate the Q&A session. So a couple questions came in already. Paul, the first one is going to be for you. What port speeds are supported on the S600?
So in the standard unit, those 4 ports, they can go at either 100 base T or gigabit, okay, speed. If you want 10 gig, we have an optional plug-in card that gives you two more ports, and they're SFP plus and they run at 10 gig. So you can actually have up to 6 ports on the device.
Excellent. This might have been touched on towards the end, but I'm going to go with it anyway. Steve, this will be for you. Would the audit server be sufficient to appease the regulatory authorities for things like the MiFID II directive?
Yes, in fact, that's what it's designed to do. It allows you to set, as I mentioned, thresholds that match whatever compliance you have. And in fact, if you have a mixed environment, like a stock trader may have to comply with both FINRA regulations in the US and MiFID II in Europe, you can set different alert thresholds for those levels. So if you have a MiFID 100 microsecond requirement, you can be alerted on that. Or you can also be alerted if machines are exceeding the 50 or single microsecond requirement of FINRA.
Okay, thank you. And Steve, another one for you, another one to do with audit server. How long does the audit server store historical data?
That's configurable. It can store it forever as long as you have enough disk space. And that's really the limiting factor. We can trim the data. You can say keep up to 7 years, for example. That's a common value that needs to be kept. You can say keep up to 7 years worth of data. Or if you're archiving that data off on your own, you can set a smaller threshold.
Okay. Paul, this one's for you. You mentioned that the S600 can protect against denial of service attacks. How does it do that?
Yeah, so that's a great question. So you saw the picture of the network ports, all those network ports connecting to an FPGA, and then the CPU sits on the other side of the FPGA. So the FPGA looks at all traffic coming in on those ports, and it bandwidth limits the bandwidth regarding how much can get to the CPU. And under just the standard operation, we do not let more, well, the specification on the product is 10,000 NTP requests per second. And if we get hammered with more than that, if it gets to 13,000, we start bandwidth limiting it. And there you have it. CPU is quite happy. It handles that no problem. And we can set alarms. For example, let's say you never expected more than 1,000 requests per second. And all of a sudden you're seeing 1,000 requests per second or 2,000 or whatever. We can send an alarm saying, hey, you're seeing more traffic. We also have a feature on there called the NTP reflector. The reflector is 100% pure hardware timestamping. It can do 360,000 packets a second, and that's, which is basically NTP at line speed. And then again, you can also set thresholds in that. So even though you're handling all requests, if you're getting more than you would expect, we can send you an alarm. So either way, you aren't going to, as we say, knock the sync server over, but you will get alarms that there's some kind of denial of service, or certainly more traffic than you expected is being sent to the box, but the box defends itself perfectly against it.
Excellent, thank you. And we have one more question. So if anybody has any, please submit them to the Q&A box at the bottom. It's again for Paul. Does the S600 support IPv6?
Yeah, sure. I mean, when you set up each LAN port, you choose either IPv6 or IPv4. No problem. So
Okay.
supported it for years.
Thank you very much. So Jenna, that is all that was in the Q&A that we have so far.
Wonderful. So thank you. Excellent. Thank you, Paul, Steve, Maroon, and Corey for that excellent presentation. I'd also like to thank our participants for joining us today. We certainly hope you found the webinar valuable and informative. And just as a reminder, a recorded version of the webinar will be sent to you within the coming days. So again, thank you, everyone. I hope everyone has a wonderful day.